Hi, my name is Quan Nguyen, and I have the privilege of presenting Pipette, improving core utilization on irregular applications through intra-core pipeline parallelism. This work was done in collaboration with my advisor, Daniel Sanchez at MIT. Please attend our live session on October 20th. We want to address the problem of irregular applications' unpredictable memory accesses and control flow. They can be found in many domains such as graph analytics, sparse linear algebra, and databases. Modern out-of-order cores suffer from poor performance and low IPC on irregular applications because they aren't able to make full use of their out-of-order core structures. To tolerate the latency of these operations, we can decouple applications into pipeline parallel stages. These stages can have fast variations in the amount of work, so we time multiplex these stages to achieve load balance. Our insight is that you can reuse out-of-order core structures to achieve both of these goals. Pipette puts these underused resources to work by implementing fine-grained pipeline parallel communication between the threads of an SMT core, and by doing so we achieve speedups of gmean 1.9x and up to 3.9x over the SMT baseline in challenging irregular benchmarks. Let's see how pipeline parallelism is a great choice for implementing irregular applications. Unpredictable accesses hurt performance. Consider this graph on the left and the array in blue at the bottom, with data for each vertex. If we want to run a function func for each neighbor of vertices 1 and 2, the code might look like this. For ngh in the neighbor list, set x to array of ngh, then do func of x. These indirect accesses to the array often miss. Now let us think about the consequences of the number of instructions in func. If func is a few instructions, say 2 to 3 instructions, then many loop iterations worth of instructions can fit in the ROV, and we can fill out the low store queues with many iterations worth of memory accesses. However, if func is long, say tens to hundreds of instructions, then today's 200 plus entry ROVs will get filled in as few as 3 iterations worth of vertices. As a result, the low store queues remain mostly empty. We see no reason why fetching the array needs to be bottlenecked by the number of instructions in func. We want to decouple these accesses from their use. By decoupling these applications into many stages, we allow the producers to run ahead of the consumer stages. This achieves latency tolerance, but also allows us to use out-of-order core structures more effectively. We want to split these applications so that each long latency operation is in its own stage. Looking back at our example code, we're concerned with a long latency indirection that's hard to prefetch well, which is the access to the array on the second line. We decouple it from the call to func by pasting the access to the array into its own stage. Now, by pipelining this loop, the first stage can fetch the array in a tight loop, and the second stage, with func, won't fill the ROV waiting on these long latency loads. Pipeline parallelism is a natural fit for this decoupled compute model. In our solution, we focus on fine-grained pipeline parallelism, where we split the program such that there are relatively few other instructions in between queue operations. This also means that the overheads from software techniques would depress throughput on these applications. Moreover, prior hardware techniques have only decoupled regular applications. Irregular applications add 2 new challenges. The first challenge is that irregular application pipelines have load imbalance. Suppose you want to create the pipeline from the previous slide by processing vertices 1 and 2 in the first stage, and processing its neighbors, the green vertices, in the second stage. The pipeline might look like this. Vertex 1 has high out degree, and therefore adds a lot of work for the second stage, whereas vertex 2 has low out degree, and contributes little work. Prior techniques cannot effectively handle these fast variations in the amount of work because computations happen on different cores. The second challenge is that irregular applications also need several stages to fully decouple all long latency indirections from each other. Our previous example had just 1 indirection and 1 array, but a more realistic application, like breadth first search, or BFS, has 3 such difficult indirections. Furthermore, it traverses several large data structures. To transform BFS into a pipeline parallel application, we identify its long latency operations, that is, these indirections, and place each one into its own stage. We turn this theory of BFS code into a multi-threaded pipeline parallel program as follows. First, we process the current fringe, shown with the red highlighted code, and corresponds to the red stage on the right. We then enumerate the neighbors of its fringe vertices, shown in orange. Then we visit those neighbors, shown in green. And then for those neighbors whose distance is not set, we set their distance and add them to the next fringe, shown in blue. As before, we organize them as a feed-forward pipeline of stages. We decouple these stages with FIFO queues, but unlike prior work, we time multiplex all of these stages onto a single multi-threaded core, reusing existing core structures to implement decoupled communication. We call our technique Pipette. Pipette has several features that enable us to excel in irregular applications. It reuses the physical register file, to build architecturally visible queues for inter-thread communication, which achieves latency tolerance. We reuse simultaneous multithreading to time multiplex many stages onto the same core, thus giving us load balance. We provide ISA primitives for fast queue operations and efficient control flow changes, as well as cheap acceleration of common access patterns, which gets us high performance. On the other hand, prior work is missing some or all of the ingredients for efficiently running irregular applications. These ingredients are having enough stages to fully decouple an application, being able to dynamically load balance work in each stage, and having flexible decoupling and control, which means having the flexibility to decouple code around long latency events. Decoupled access execute and its descendants split a single processor into separate access and execute processors decoupled with queues. With only 2 stages, though, they are prone to type data dependencies that cause loss of decoupling and low performance. It also forces us to make unnatural divisions as we separate code into separate access and execute programs. Streaming multi-core systems, such as RAW and MPPA, use many more interconnected cores, but because stages are statically mapped to cores, they cannot dynamically load balance the fast varying work per stage that arises from running irregular applications. They're also limited in the way that they can communicate control flow between cores. Decoupled multithreaded cores, such as Outrider and DSWP, also lack the control flow mechanisms that are needed to accelerate irregular applications. Finally, data structure fetchers and prefetchers, such as HATs and IMP, are highly domain-specific and come with substantial area and power overheads. Here's why Pipette features are important. We show a speedup plot on the left and instructions per cycle, or IPC, on the right. For both, higher is better. We run BFS on a large row graph with a 6-wide out-of-order core with aggressively sized speculation structures. Here we see that serial, which is normalized to 1, has an IPC of barely 0.5. Pipette, running on a single multi-threaded core, shown here with blue bars, has significant speedups of nearly 5x over serial, with an IPC of 2.4. Now let us examine a data parallel implementation running on a 4-threaded core. The orange bars show that using SMT alone is not enough, with about a 1.5x speedup over serial and an IPC of just under 1.0. Part of this slowdown arises from the increased pressure on the memory system and synchronization overheads. Finally, we represent prior work with the streaming multi-core implementation, shown here with the yellow bars. Although the speedups are comparable to Pipette, we do so by using nearly 4 times the area, and per-core utilization remains quite poor. Pipette does best overall with just a single multi-threaded core. Now let's see how Pipette works. Starting from a multi-core system, we show how Pipette fits into a modern out-of-order core. Zooming into one of these cores, we see that we only make minor changes, highlighted in purple, to implement Pipette. The Pipette ISA maps architectural registers to architectural queues, so that a register write corresponds to an NQ and a register read corresponds to a DQ. Queue operations are very frequent. In BFS, for example, 1 in every 6 microops or so is a queue operation. So Pipette's implicit NQ and DQ semantics reduce instruction overheads. Let's see how this works. One of Pipette's instructions, map NQ, takes a queue and a register. In this case, Q1 is a queue and R3 is a register. It maps every write of register R3 as an NQ of Q1. Another Pipette instruction, map DQ, maps every read of R4 as a DQ of Q2. These instructions need to be run only once to set up a pipeline. Any subsequent instructions using R3 and R4 now manipulate Q1 and Q2. So that an instruction that reads R4, adds 5 to it, and writes it to R3 corresponds to a DQ of Q2, adds 5 to it, and NQs it into Q1. We notice that register renaming already uses a lot of queue-like structures. For example, when we allocate a register, we DQ a register from the free list, and when we commit an instruction, we enqueue the newly freed physical register IDs back to the free list. We may as well use it to build actual queues. One of Pipette's key features is its reuse of the physical register file, or PRF, to build queues. We observe that the PRF is underutilized in irregular applications. When you decouple applications, the PRF becomes much more lightly used. Again, this large pool of registers is already managed by structures like the free list, which already have queue-like semantics. Our insight is that we can reuse these structures to build queues. We do this with the queue register map, which tracks the physical register indices used by all the queues in the system at very low cost, with just a few hundred bytes of storage. Let's zoom into one of these queues. Each queue stores a series of physical register indices as well as a control value bit, which we will discuss shortly. Whenever we perform an NQ, the renamer sends a physical register ID from the free list that will contain the NQ'd value. The QRM now tracks the physical register as part of the queue. Whenever we perform a DQ and commit it, the QRM releases the physical register ID back to the free list. In this diagram, the queue grows towards the right, and pointers wrap around when we reach the end of our allocated space in the QRM. All right, we've seen how Pipette provides architecturally visible queues. Now let's see how to accomplish inter-thread control flow. Sometimes a producer may want to tell the consumer to move on to the next part of the input. We achieve this by sending a specially marked value to the consumer. Pipette adds hardware support to make changing control flow efficient. So we use control values, which is indicated by the control value bit in the QRM, combined with a DQ control handler. When a consumer tries to DQ a value with the control bit set, it instead jumps to a DQ control handler, similar to an exception handler, to change control flow. We may also have the reverse case, in which the consumer wants to tell the producer that it is no longer producing useful data. In this case, we have an NQ control handler, so that whenever a producer tries to NQ a value to the consumer, it instead jumps to an NQ control handler and moves on to the next part of the input. To show how a control value works, let's take another look at BFS. BFS has very infrequent fringe changes that need to be communicated to the last stage after it processes all vertices at the current distance, in this case, 3. Rather than communicate through memory, we use a control value passed through these queues. When we move on to the next fringe, we set a new current distance, 4, and then we send a control value. DQ control handlers in the intermediate stages pass along this control value. The last stage's DQ control handler changes the fringe and moves on to the new current distance of 4. Pipette also further accelerates common access patterns. We observe that memory access patterns are actually easy to compute, even if they result in long latency accesses. So we can further decouple these long latency accesses with reference accelerators, or RAs, which integrate into the existing queue interface provided by Pipette. On the left-hand side here, I'm showing the case without RAs, in which the producer sends an address to the memory and then queues the data to the consumer after receiving that value. But if you add RAs, the producer instead simply enqueues the address to the RA, and the RA performs the fetch for us. This improves decoupling at low overhead without filling the load or store queues, as these fetches are now non-speculative. Finally, let's move on to the evaluation. We use event-driven cycle-level simulation, and our core model is a 6-wide out-of-order core similar to Intel Skylake in size to accommodate our additional threads. Our baseline is a data parallel 4-way multi-threaded system, and for an additional comparison, we want to compare to a 4-core single-threaded streaming multi-core system. Because we want to measure the impact of load imbalance, we include Pipette's features, including reference accelerators, even though those are our contributions. We evaluate several applications, from graph analytics, sparse linear algebra, as well as databases. In this slide, we show G-mean speedup for all 4 of our evaluated systems, showing just BFS at first. Higher is better. We normalize our speedups to the data parallel baseline, the orange bar. We see that the data parallel system does not improve much over the serial 1-core, 1-thread implementation, shown with the red bar. Pipette, the blue bar, achieves significant speedups over the data parallel baseline. While the streaming multi-core system does better, it does so with 4 times the cores. The remaining applications show similar trends in speedup. And when you look at speedup per core, Pipette speedups especially shine compared to the streaming multi-core implementation. To better understand these performance differences, I show how our evaluated systems spend their cycles, normalized to data parallel, first showing just BFS. Here, lower is better. These bars are divided into 4 sections. The bottom section, in blue, represents cycles spent issuing instructions and doing useful work. Above those, the red sections represent back installs, such as waiting on memory accesses and out-of-order core structures becoming full. In Pipette and streaming multi-core, the purple section represents cycles spent waiting on queues that are full or empty. Pipette, the third bar, labeled P, reduces the impact of memory latency, as shown by its smaller red bars, and also outperforms the streaming multi-core system by better managing load balance, as shown by the smaller purple bars. These observations also hold for the other applications. We also explored cross-core communication with a multi-core, multi-threaded implementation of BFS. We can take our single-core, 4-threaded BFS and replicate it across 4 cores. We partitioned the graph across 4 cores, with each core responsible for updating its part of the graph. The fetch distances stage in green in each core sends its vertices to the appropriate core based on vertex ID. This avoids the need for synchronization across shared memory. Our results of running this BFS on several graph inputs show that Pipette outperforms the multi-core, multi-threaded data parallel baseline in most cases, and achieves the best G-mean speedup overall of 6x. We have many more details in our paper, including how we reuse the out-of-order core, synthesis results for key components, and information on Pipette's low implementation costs. Our additional analyses show that Pipette also saves up to 2x in energy, and its speedups are durable even if you change the number of stages and the size of the cores. In conclusion, we showed that irregular applications hamper core utilization. Our technique Pipette reuses out-of-order core structures to efficiently implement irregular applications as pipeline parallel programs running on a single multi-threaded core. We achieve speedups of gmean 1.9x and up to 3.9x over the S&T baseline in several challenging irregular benchmarks. Thank you, and please join us for our live session on October 20th.